So, ladies and gentlemen, welcome. Welcome at the second part of Enzymology lesson on kinetics, enzyme kinetics. And today we will, we will have a look at erase. Yes, we will have a look at first a little bit repeating. And we will look at how we can determine Km and Vmax. So imagine the situation that you have an enzyme sample, you have a substrate, and you want to determine the Vmax of the enzyme and Km of the enzyme. And this is somehow related to the second application, which I will be talking mostly about today. And this is inhibition of enzymes. So this is especially important for drug design. So let's start with the enzyme kinetics and standard Michaelis-Menten behavior. So on the axis there is a rate of reaction. On the horizontal axis there is the concentration of substrate. And the profile of these relationships looks like this. Sorry, that should be straight or almost straight, and this is somehow converging towards the value of Vmax. And I also explained last time that if you take a half of Vmax and you follow like horizontally to the point on the curve and then vertically down, you get to the Km, Michaelis constant. And now how we can measure this? So we are interested in determining Km and Vmax, and we want to measure it. So usually the standard scenario which is mostly used is that you prepare a series of experiments in which you mix the same amount of enzyme with different concentration of the substrate. So here there could be some concentrations of substrate, because you have some either stock solution of the substrate or you have some substrate in a solid form. You can prepare mixtures with different concentration of substrate, and then you add enzyme. So you have to, of course, like calculate the concentration at given like dilution by the enzyme, and you measure some values of rate, and you can plot them into this plot. And I try to like this is the purpose, so to draw it in a way that they are not perfectly lying on the curve, but they are somehow distributed around the curve due to the fact that any measurement is not 100% accurate. So you get something like this red points, and you want to like determine the shape of the curve, which is that you want to determine the value of Vmax and the value of Kn. And how we can do that? So today with computers with in our hands, we can use nonlinear fitting. So there are many different programs for nonlinear fitting. It's possible to use, for example, simply Excel, where you it's quite simple. So in one row in Excel you write concentrations of substrate, so you get different values of concentrations of substrate. Then in a second row you calculate plot the rate. So these are concentration substrate that you pre-mixed for the experiment. This is what you measured. We will talk about different methods for assays of enzyme activity, so this will be in a next lecture, and we will go enzyme by enzyme, group by group, method by method to show which methods can be used. At the end, here you calculate like a V, how to call it, like the function of concentration of substrate. This works in a way that you can imagine this is an Excel. So in some box here, you put some estimate of the Vmax. So for example, if you can immediately look at the plot, and you can estimate that Vmax is going to be somewhere in this area, so you can make some estimate, for example here. So let's say this will be 1, I don't know what unit it is, could be some rate, so the estimate would be 1, and this is the estimate of Vmax. And here in another cell we can have estimate of Km, so this will be, let's say, 2.5. Doesn't have to be really accurate. So you can somehow estimate and put it into two units in a spreadsheet, for example in Excel. And then you can calculate, you can use the Michaelis-Menten equation. So the equation is that V is equal to V max multiplied by concentration of substrate divided by Km plus concentration of substrate. And here we got the concentration of substrate. So for example, for this value and this equation, you use this value here, this value for Vmax, and this value for Km, and from this you calculate some rate. And if you set these estimates properly, you should be very close to this value. But if you are not close, if it's not perfect, doesn't matter at this moment. So now in the next step you calculate like the V minus V, this function. I will not draw it again, so it's this value. So you subtract these two values and calculate the square. So this is values you get here, and you somehow copy these units down. So here you got like a square error of your model. And here you make a sum of these values and you put it into this column. And now in Excel there is a simple like a plugin, or how to call it, which is called solver. So you start solver in a menu, you choose what is the cost function, or how to I don't know how it's exactly called in solver, but what is the error function. It's this value, the sum of errors, something that you want to minimize. Then you have to choose whether you want to minimize this or maximize this. So of course we want to minimize the error, so you choose that you want to minimize it, and then you have to choose the values which are going to be altered, which are going to be changed, and this is the Vmax and Km, these two values. And then you press some button like submit or solve, or however it is called, and it will calculate for a short moment, and at the end these values will change a little bit. So this will change from 1 to, for example, here a little bit like 0.95, and this will change from 2.5 to, let's say, 2.3 something. So these values are quite good estimates of the of the Michaelis constant and Vmax. It's also possible to somehow evaluate it in some statistical program or some statistical approach to get like not only like the estimate of Vmax and Km, but also some like error bars, some standard deviation, standard error estimate. So this could be quite useful. You can of course use some, I don't know if you are familiar with some statistical software. So for example, if you want to use R, it's quite popular in molecular biology, bioinformatics. So in R there is for linear model it's LM, and for nonlinear model is NLS or something. NLS, nonlinear least square model. So there is function using which you can do the same job, and the additional important info is that you get not only like Vmax and Km, but you get also like Vmax and Km plus minus some standard error. So this is how we can measure the value of Vmax and Km, and if we know the Vmax and Km, so we can somehow predict that if the concentration of substrate is somewhere here, we can predict that the rate is going to be something like this. Or in principle, if you have some, for example, some biotechnology process and you want to use enzyme to decompose some substrate from some bioreactor, and you know what is the concentration of the of the substrate in the bioreactor, it's possible to somehow like not only to predict the rate at the moment when you like start the reaction, but because the substrate concentration will go down because of the enzyme being converted by the substrate being converted by the enzyme. You can also follow like on this curve what would be the rate and how the rate will go down, and from this you can somehow predict how long it would take for the whole process to proceed, or how long it would take to get under certain concentration, for example. So this is the purpose why we study enzyme kinetics, and the next purpose, which is inhibition, I will show in shortly. But before I start with inhibition, I want to also explain like normally we got the relationship that on the x-axis we got concentration of substrate. Here we got the rate of reaction, and we should get something like that with the Vmax, and here Km, and here is Vmax. And it's possible to use what I previously explained, like to measure rate at different concentrations. You can prepare a solution with certain concentrations, so this is simply like some pipetting job, and you can measure the rate of reaction, as I will show in the next lesson. And then you can use some nonlinear fitting to fit this model. And for nonlinear fitting, it's very useful to have some computer, because you have to make some like trials and errors, or what the computer does is that it makes some trials and errors and trying to somehow move this line up and down. So it's trying to change like to increase to decrease Km if the line is too much this way, or to decrease Km if so increase Km if it's too much this way, or to increase Vmax if it goes too high, or too low, or decrease if it goes other way around. And it needs some computer for doing this. But some time ago the computers were not really available, so as an alternative solution it was developed that if you look at the equation, V is equal to V max, concentration of substrate, divided by Km plus concentration of substrate. So this is like nonlinear relationship. But if we swap this, if we make some reciprocal values, we get something like that the reciprocal rate of reaction. So if you take 1 divided by rate of reaction is equal to Km plus concentration of substrate divided by V max, concentration of substrate, and we can also rewrite it like that it's equal to Km divided by V max divided by concentration of substrate plus 1 divided by V max. And this is like it's possible to simplify this, so in a way that 1 divided by V is equal to like 1 divided by concentration of substrate plus some constant. So if you look at this relationship as a relationship not between concentration of substrate and rate, but a reciprocal concentration of substrate, 1 divided by concentration of substrate, and reciprocal rate, 1 divided by rate, you get something like that. So it's like linear relationship, and you can also like plot it. So we will have like horizontal and vertical axis. So here on vertical axis is now, instead of rate, 1 divided by rate. So here, like at the 0 value, there is like a infinite rate, and here is here is very small rate of the reaction. And also here we will have like concentration of substrate, but again it's like reciprocal. So here is like infinite concentration of substrate, and when we go this way the concentration of substrate goes down. And if you take these points, I will switch the color. So if you take these points which we plotted here and you plot them in this reciprocal space, they should be like on one line more or less. Of course they will be not exactly on one line due to error, and if you fit them you should get some line like this, and it crosses the vertical axis and horizontal axis in 2 points. This point is 1 divided by V max, so it's this value. Then the slope of the equation is Km divided by V max, and if you somehow set that this is equal to 0, this is equal to 0, and you determine what is the concentration of substrate, then you get that the concentration of substrate is minus 1 divided by Km. Sorry, this is So this is very simple like tool for making determining the value of Km and Vmax, and it has been historically very often used because in a time when there were not so big access to computers, it was much easier to like calculate the reciprocal value on some calculator and then do some linear fitting, for which you need just a simple equation, rather than doing like a complicated nonlinear fitting. So it seems like today this kind of plot may be useless because we have computers and we can use nonlinear regression. Nonlinear regression is furthermore like more accurate, more robust, because here when we have some some error at a low concentration of substrate, so this is here, low concentration of substrate is here, so small error here in a concentration manifests much more than small error in concentration here at a high concentration of substrate, and the same is with rate, so small error of rate measurement is here like manifested more than here at high concentration and high rate. So this linearized plots are like introducing some error, and this is the price which is paid for their for the simplicity of their use. So today it's much better to use like a nonlinear regression, what I explained in a previous slide using for example Microsoft Excel, and I would say that there are two like main messages that we can get from these linearized plots, beside the fact that they are very simple for application and do not need some computer. One of them is the fact that it's always good to have like quite equidistant distribution here in this reciprocal space to get good measurement, to get accurate results. This works fine if you have like equidistant points, the same distances here, then your measurement is quite accurate. But this means that here you should not have the equidistant, because it's this is like a concentration, but in a previous slide it was like reciprocal concentration. So it's always better, instead of if you design an experiment and you want to decide which concentration of substrate you would choose and prepare such solutions. So normally people think about like 1, 2, 3, 4, 5, etc. And this is not optimal, because this is like equidistant concentrations, but if you put like reciprocal values, they are not equidistant anymore. So it's always better to use something like 0.5, 1, and then 2, and then 4, and then 8, and to use some multiplied value. So then if you like plot these values into the reciprocal, on the reciprocal axis, on the reciprocal scale, you would get like here there would be 8, or 1 divided by 8 to be more accurate. This is 1 divided by 4, 1 divided by 2, 1 divided by 1, so 1, and there will be 2. And the second message from this reciprocal plots is that they are quite useful in some visualization. So people who have been studying enzymology for a long time and they are used to this type of plot, they are quite happy if you plot it this way, because from this it's possible to somehow recognize, so okay, so this is like a normal kinetics, but for example when you got some points here and here and here, then they recognize simply that it's any inhibition of substrate, and then you can have some different plots for if you add some inhibitor, this somehow alters this shape of this curve, or if you add if you have some two substrate reaction and you change concentration of one substrate and you keep the concentration of second substrate constant, then you do this other way around. So from these shapes some people can somehow recognize what's going on and what kind of kinetic model the system follows. So for some people it's very illustrative and much more illustrative than these original plots where you have a rate as a function of concentration of substrate. Besides this double reciprocal plot, which is called a Lineweaver-Burk plot. So beside this Lineweaver-Burk plot, I will plot it again. So here is the reciprocal concentration of substrate. Here is the reciprocal rate of reaction, and you get curve like this. And here you got 1 divided by V max, and here you got minus 1 divided by Km. So this is Lineweaver-Burk plot, and there are also some others. So it's possible to plot on the horizontal axis, you plot the rate, and on the horizontal axis you plot the rate divided by concentration of substrate, and you got points like this. So this is called Eddy-Hofstee plot, and here this approaches to 0 at the point which is equal to Vmax, and from the slope is minus slope is equal to minus 1 divided by Km. This is so-called Eddy and Hofstee plot, and there is also Haynes plot, which looks like that you got here concentration of substrate. Here you got the concentration of substrate divided by rate, and you got again something like this. So here you got some values. Here the value is, I don't know, here it's minus Km, and the slope is minus 1 divided by Vmax. Sorry, plus 1, because it's increasing. Sorry. So this is Haynes plot, and this one is the far more common. Once I always, when I teach enzymology, I give some homework where there are some simulated data, and the task for the students is to take this simulated data and to determine the value of Vmax and Km. And once I had such an idea that I asked them to do it by all these three methods, and also by nonlinear regression. And they were also asked to determine the errors. So here you make some non-linear, by some linear regression. So there is simple, like a simple equation for getting errors for a linear regression, and then you can somehow like convert this error of the slope and the this value to the errors of Vmax and Km. And the result was that when the task was easy, so there was some like nice data which could be quite easily fitted perfectly, then I would say all these methods, like nonlinear as well as these three linearized methods, worked very well. If this data were a little bit more noisy, or not such noisy, but were more noisy, then it may happen that some of these nonlinear plots failed. So that, for example, one of them or two of them worked, but one of them failed. And especially if you have, for example, very high Km, which means that you got almost linear growth here, or if you have very high Vmax, so it means that like you got here some measurements which are quite useless for determination of Km, because this is determined mostly from this part and you have just few values here. So in such a complicated situation, again, like some of these models, like these linearized plots, failed. Some of them worked, some of them failed, and it was quite difficult to predict which one works well, which one fails. But the nonlinear regression was the far more robust. It worked in the most scenarios. I would also mention here something which is called an integrated Michaelis-Menten equation. So for this I will switch for a new slide. So I mentioned that the most common way how to measure Vmax and Km is to somehow prepare different solutions of substrate at a different concentration, and then you run the reaction, you measure the rate of reaction, and you determine the Km and Vmax, for example, by this nonlinear regression. So I will draw it quickly here. What we suppose here is that when we mix, when we prepare the solution with such a concentration and we run the reaction, so this means that this concentration of substrate is like because the substrate is being converted to product, its concentration goes down. But we assume that this reaction is so slow, the rate is so low, that this change in concentration here is very, very small. So when we start from this concentration for this point, then after at the end of reaction it has moved only very, very little, so we can neglect this movement and we can assume that during the whole reaction the concentration of substrate was more or less the same. And in a so-called integrated Michaelis-Menten method, or Michaelis-Menten kinetics, instead of measurement of this equation, so here there was a concentration of substrate and then here was the rate of reaction. So here we start from certain concentration of substrate and we follow its evolution in time. So we got, because the substrate is being decomposed, so we get some curve like this. In this scenario, we in this measurement, in this type of assay, we assume that the change in concentration of substrate during the reaction is very, very small, and we can neglect it. But here the this is one experiment, one reaction. So, and from this reaction we at different times either we do some continuous measurement like using some optical method, or we take some little bit of sample and we measure concentration of substrate. So here during these different time points, this concentration really goes drastically down. And how we can get the Vmax and Km from this? So this Vmax and Km is somehow like encoded in this shape of the curve. So if there is such a kinetics that you got quite high Km, so this is like kinetics with quite high Km, it means that when this starting concentration is this one, this is equal to this. So when we start, the reaction is almost, so this should not go down, so it's, sorry for drawing not perfectly geometrically, but the rate of reaction is almost 100%, almost at the Vmax. So here it goes very quickly down, but as we get to concentration, so here we get this axis is the same as this axis. So when we get, for example, somewhere here, we got somewhere here. So here the rate is already smaller, and when we go further down, the rate will go slowly, like fade away. And now imagine the same plot for the enzyme with very small Km. So it means that the plot looks like something like that. So at very low concentration it reaches almost to the Km. So here is, because this is Vmax half, so Km would be very small value. So here the rate at the beginning would be the same. So here the slope is the same, but then because here and here and here and here the rate of reaction is more or less the same, so this would follow almost a linear trend, and at these very tiny concentrations which correspond to these values, it will somehow slow down and follow like to the zero. So the difference between this and this is that this is much higher, much lower value of Km. This is much higher value of Km. The value of Vmax is approximately the same. So now it's possible to somehow fit this equation and fit this equation, and from this it will be possible to determine the Vmax and Km. The only problem is that this is a differential equation. So what we we can write that V is equal to Vmax multiplied by concentration of substrate divided by Km plus concentration of substrate, and we can also rewrite it that the rate of reaction is the rate at which the concentration of substrate decreases, so it's derivative as a function of time. So we can rewrite it in a way that derivative of concentration of substrate equals to minus V max concentration of substrate divided by Km plus concentration of substrate dt. And this is a differential equation, so if we somehow integrate it, we would be able to get some like equation by which we can fit these two profiles. Unfortunately, this cannot be like integrated analytically. It's not possible to get such a nice equation to cover all this. So there are two possible like workarounds how to solve this. Either it's possible to get something which is called integrated Michaelis-Menten kinetics, but the problem is that this is like it's not possible to integrate this to get such a, what we get is like to get like a concentration of substrate as a function of time is what we get. Unfortunately, this is not possible to do it like by some analytical integration. So unfortunately, what we can get is like a reverse equation, like concentration of substrate, time as a function of concentration of substrate. So this is quite stupid, but it's still like possible to use it. So like you have to imagine that this plot you somehow like flip it to replace, to put the this concentration of substrate on a horizontal and the time on the vertical axis, and then you can fit it. So this is one possibility, and the second possibility is again like based on some computing. So of course you can somehow fit this equation by some numerical method. So there are different methods for numerical integration. So if we want to get some very simple hint, so if you go again to Excel, then you can somehow put some like time. Then here you got concentration of substrate. Here you got the C substrate, like this concentration which was in the reaction mixture at the beginning, this value. So this will be here. And then here you add, so again you can put here some box with Vmax estimate, box with a Km estimate, and then here you can calculate like this is the this is equal to this previous value, so this value minus, and now Vmax, you can link it to this cell multiplied by concentration of substrate, so it will be again this value, and divided by Km will go again from here, and this plus concentration of substrate will be again this value, and then you can again like copy down these cells. So from the reaction or from the state in time 0, it will calculate the state in time in the first time step, and then in the second time step, and so forth. And here it was also necessary to multiply it by time step, like I will call it H, like time step. So you have to set this time step small enough, because otherwise if you use too high time step, then you would get like too coarse representation, and this would not work very well. Again, you can here like calculate, you can here set some measured concentration of substrate, so this would be calculated from the model. Here you can have another column with the measured concentration of substrate, then you can calculate the error and the square of errors, sum of square of errors, and then you can use again the solver to make to choose the best value of Vmax and Km. There is one tricky thing about it, and this is that there could be some enzymes which can be inhibited by the product. So if there is too high concentration of product, which is the case of the end of reaction, the product could slow down the reaction, and it can cause this kind of effect of slowing down. But this is not because of having high Km, but this is because of having high concentration of product. So this is the integrated Michaelis-Menten kinetics, and you can maybe find it useful. And now the most important part of enzyme kinetics, and this is inhibition. So when we talk about enzyme inhibitors, enzyme inhibitors are usually small molecule compounds, but it could be also some peptides or proteins, and they somehow interact with the enzyme, and they cause that the enzyme activity is increased. And we can somehow divide inhibitors into two main classes. So one class would be reversible, and the second one would be irreversible. Sometimes some people use like a reversible as a equivalent to non-covalent, and irreversible as covalent. So non-covalent and covalent is pretty clear. That means that the either the inhibitor binds on the enzyme by non-covalent interactions or by some covalent bonds. But I believe that this equivalency is not 100% true for both examples. It's possible to find some irreversible non-covalent inhibitor and inhibitors and reversible covalent inhibitors. And example of a irreversible non-covalent inhibitor is simply some inhibitor which is very, very strong. So if it binds to the enzyme in a reasonable time, it cannot unbind. And there would be some examples of such inhibitors maybe, and I talk about the story of different inhibitors as drugs, and I will come across some such examples. And the second possibility is that a reversible, there could be some covalent reversible inhibitor. So there are some covalent bonds which are reversible in biological environment. So for example, Schiff base. Schiff base is like if you have some aldehyde plus some amino group, it gives this plus water. So this is a Schiff base, and formation of Schiff base is very often like a reversible reaction. So this Schiff base could be formed and then could be released. So I can imagine that there could be some some compound with some aldehyde moiety, for example, which binds to some enzyme with amino groups. So for example, side chain of lysine, and it can bind by this Schiff base to form such a covalent bond, and this can block the enzyme activity. but it can be somehow reverted by reaction with water. It can be again hydrolyzed, and this would be a covalent but a reversible inhibitor. But in most cases, like inhibitors which are reversible are at the same time non-covalent, and irreversible are mostly like covalent. So I would say that I guess something like maybe 80%, 90% of different drugs act as a reversible non-covalent inhibitors, and some 10%, maybe 20% are irreversible covalent inhibitors. But I will show some examples in one of the lectures. And now, when we have these non-covalent inhibitors, we can further classify them into some 3 groups, and the first one would be competitive, the second one would be non-competitive, and the last one would be uncompetitive. So it's uncompetitive in Czech, so sorry that I accidentally used Czech, so it's uncompetitive in English. And there could be some mixed or some more complicated, but we will focus on these three types. So let's start with the competitive inhibitors. So what happens is that we can again start with this a reaction. So we got a reaction of enzyme with substrate, gives the enzyme substrate complex, and this gives product, enzyme plus product. And here we got K2, we got K1, and here K minus 1. And this is like uninhibited reaction. And a competitive inhibitor is a compound which binds onto free enzyme, not onto the enzyme substrate complex, but only onto the free enzyme. And it creates the enzyme inhibitor complex. And because it's reversible, I have to make this arrow here. And I will not use here like some rate constant, because it is not useful anymore. It would be possible to use some small letter ki1 and small letter ki minus 1, but it is not really useful. And instead I will use here a ki, like capital Ki, or again you can see often Ki if people are lazy to write it as a subscript, so they write it as a Ki. And the Ki is a dissociation constant of this enzyme inhibitor complex. So the Ki is equal to like concentration of free enzyme multiplied by concentration of inhibitor divided by concentration of enzyme inhibitor complex. So now how we can proceed to get some like insight into kinetics. So usually what we want to measure is this value of Ki. For example, if we try to develop some new drug, and this drug acts as an enzyme inhibitor, what is very important for us is the value of Ki. And then if we get some compound which has very low Ki, which means that it's very potent inhibitor, then we can somehow go to some conference and give a talk that we developed some inhibitor with Ki equal to some very small number, and everybody will be amazed. So why small number? Because if the enzyme, if the inhibitor is really very strong, it means that if we mix enzyme and inhibitor in just a simple like mixture in a test tube, we add enzyme and we add inhibitor, and we leave this mixture to somehow equilibrate. So at some after when we get to the equilibrium and we measure these concentrations and we put them into this equation, we should get the Ki. And if the inhibitor is really very, very strong, it means that there will be almost 100% of the enzyme in this enzyme inhibitor complex, and only tiny value, a tiny amount, there will be only a very small concentration of the free enzyme. If the enzyme if the inhibitor binds weakly, it means that there will be some good, some high amount of this free enzyme, because this interaction is not so strong. If the inhibitor is very strong, it will bind to all the enzyme, and there will be only very, very small concentration of the free enzyme. This Ki is usually like, because it's like concentration multiplied by concentration divided by concentration, the Ki is often expressed in concentration units. So you can get something like that's 5 micromole per milliliter or even micromolar. So from the physical chemical point of view, some hardcore physical chemists do not like this, because they use these concentrations like that they are divided by 1 mole per liter. So these are like without any units. So also Ki is without any units. So some physical chemist would prefer to say that it's 5 multiplied by 10 to minus 6. And but in for example drug discovery, in medicinal chemistry, people who develop some inhibitors, because it's practical, they use these concentration units, and you can hear that some inhibitor is micromolar, that some inhibitor is nanomolar, that some inhibitor is picomolar, or something like that. So if you imagine like having some millimolar inhibitor, means that because if you add inhibitor to the cell of patient, and you add it in the concentration like very close to the Ki, you get like, if the concentration of the inhibitor is equal to Ki, this is equal to this, means that this is equal to this. So it means that like you have 50% of enzyme like in the free form, and 50% of enzyme in the complex, which means that if you have some millimolar inhibitor and you add it in a millimolar concentration to some mixture, then you got some 50% effect. And if you add more inhibitor, you got more than 50% effect. If you add less inhibitor, you got less than 50% effect. And so, for example, if you have millimolar inhibitor and you want to make it like efficient to inhibit enzyme by 90%, it would be necessary to add more than a millimolar concentration. So, for example, 10 millimolar concentration. And if you imagine like that, most drugs have something like molecular weight is equal to something like 500 moles per liter. Grams per mole. It's a molecular weight of, like, most drugs are something like 300, 400, 500 grams per mole. And if you imagine like you got 10 millimolar concentration, so it's 0.01, you got something like that you need 5 grams per liter. And if you have some patient with some, I don't know how much blood is, something like 6 liters, so you end up that you need some 30 grams. So imagine some patient has to eat 30 grams of some pills. It's nonsense. It's a murder. So such a drug would have a lot of side effects, because any drug can have any side effect. And if you administer it such a high concentration, then there is very probable that such side effects will manifest. So instead, drugs must be something like micromolar inhibitors, or even better, nanomolar. So I would say that most drugs today are like nanomolar inhibitors, and time to time you can see some picomolar inhibitors, and femtomolar it's very, very rare. So I would say that most like drug discovery works in this range. So this is like where most drugs fall in terms of their affinity to the enzyme or some other target. So, and I will continue. I will maybe write down this equation again. So we got like enzyme plus substrate. This makes enzyme substrate complex, and this can decompose to enzyme plus product. Here we got K2, here we got K1, here we got K minus 1, and enzyme can bind with the inhibitor, to form enzyme inhibitor complex, and there is this Ki is equal to concentration of free inhibitor, concentration of enzyme divided by concentration of complex. So, and now how we can use it to like determine the kinetics. So if you remember last time when we somehow developed the Michaelis-Menten equation, we worked with some total concentration of enzyme, and in this case it was like concentration of free enzyme plus concentration of enzyme substrate complex. This is how it was in the previous lesson without an inhibitor. So here we also add enzyme inhibitor complex. So the total concentration is sum of these concentration, or in the other words, enzyme can be either free or with bound substrate or with bound inhibitor. So now we somehow like introduce this equation here, so we can multiply like both sides of equation by concentration of complex enzyme inhibitor and divide by Ki. So we will just swap these two symbols. So we can write that Ce is equal to concentration of free enzyme plus concentration of enzyme substrate inhibitor, enzyme substrate complex plus concentration of inhibitor multiplied by concentration of enzyme divided by Ki. And we can simplify it, that it's equal to, I will write first this enzyme substrate complex, so it's enzyme substrate complex plus, and now I will put this outside the bracket, and this will be 1, this is this one, plus concentration of inhibitor divided by Ki. And we will use this bracket, this kind of magic bracket, in all three types of inhibition. So in the previous time we had something like that, the change of concentration of enzyme substrate complex with the time is equal to K1, concentration of enzyme, multiplied by concentration of substrate, and now it will be minus, and there was K minus 1 plus K2 multiplied by concentration of enzyme substrate complex, and this was equal to 0 because of the steady state. So it means that if the reaction is somehow already running, then the rate by which this enzyme substrate complex is being formed is the same as the rate as it is being decomposed. So this is the equation, and we can somehow insert here this. So we got we will better put this free enzyme here. So we can also work with this equation. So we will get something like that concentration of free enzyme is equal to this minus this. So it will be concentration of enzyme substrate complex minus concentration of free enzyme divided by 1 plus the concentration of inhibitor divided by Ki. Is it correct? Let me quickly check it. So no, this is swapped. Sorry, I apologize. So it should be Ce minus concentration of enzyme substrate complex. So we first subtract this, and then we divide by this. Okay, so that's perfect. So now we got like that K1, and then all these brackets, Ce minus concentration of enzyme substrate complex divided by 1 plus concentration of inhibitor divided by Ki is equal to, I can write it that it's equal to K minus 1 plus K2 and multiplied by concentration of enzyme substrate complex. So, and now we are at the end of the paper. Sorry. So how we can now proceed? So I think it's good idea to somehow like rewrite this bracket. So it's K1 Ce divided by 1 plus concentration of inhibitor divided by Ki minus concentration of enzyme substrate complex, I forgot K1, divided by 1 plus concentration of inhibitor divided by Ki, and this is equal to K minus 1 plus K2 multiplied by concentration of enzyme substrate complex. And now I will have to go for a new paper. So I will switch to a new paper. So here it was K1 Ce divided by 1 plus concentration of inhibitor divided by Ki. Let me check it. Yes, and I can write that it's equal to so this will be equal to and then there was K1, concentration of enzyme substrate complex, divided by 1 plus concentration of inhibitor divided by Ki, plus K minus 1 plus K2, concentration of enzyme substrate complex. So this is K1 Ce divided by 1 plus concentration of inhibitor Ki is equal to, and now K1 divided by 1 plus concentration of inhibitor divided by Ki plus K minus 1 plus K2, and this multiplied by concentration of enzyme substrate complex. And then if we want a concentration of enzyme substrate complex is equal to K1 Ce divided by 1 plus K concentration of inhibitor divided by Ki, and this will be divided by K1 divided by 1 plus concentration of inhibitor divided by Ki plus K minus 1 plus K2. I somehow lost concentration of substrate everywhere. Yes, I lost here concentration of substrate. Sorry. As well as here, as well as here. So now I have to put it here and here. Sorry again. And so now we got concentration of substrate here and concentration of substrate here and concentration of substrate here and the concentration of substrate here. So now what we do is first we divide like both parts of equation, like we will divide by K minus K1. So here nothing will change, so it will be complex enzyme substrate, and it's equal to, we will divide this by K1 and this by K1 and this by K1, so we will get Ce multiplied by concentration of substrate divided by 1 plus concentration of inhibitor divided by Ki, and this is divided by concentration of substrate divided by 1 plus concentration of inhibitor divided by Ki plus, and now it will be K minus 1 plus K2 divided by K1. And now we will multiply again both these parts by 1 plus concentration of inhibitor. So maybe I can do it like directly here. So if we multiply this, we will simply remove this part, and this will be multiplied by 1 plus concentration of inhibitor divided by Ki. And now finally, if you remember from the last time, we to get the rate of reaction, we had to multiply by K2. So here we multiply by K2, and what we get is that K2 multiplied by Ce is, if you remember properly from the last time, so it is the K, so it is Vmax. Here we got just the concentration of substrate plus, and this is the Km. And if we rewrite it, what we get is that the V is equal to V max multiplied by concentration of substrate divided by concentration of substrate plus Km, and this Km is multiplied by 1 plus concentration of inhibitor divided by Ki. So this is like a standard Michaelis-Menten equation, except that Michaelis-Menten constant is multiplied by this bracket, which I called previously a magic bracket. So now let's imagine that we set the concentration of inhibitor equal to 0. So if this is 0, this is also 0, and this is 1, so it's standard Michaelis-Menten equation. And if we increase the concentration of inhibitor, it means that the value of Km, like we call it like apparent Km prime, which is equal to Km multiplied by this magic bracket. So this Km is rising, and if we look, I have to switch a new paper. I will switch color. So if we again look at some plot in which we get like concentration of substrate and the rate of reaction, and we get such a profile for uninhibited reaction. So in the presence of inhibitor, we will get like this is very low concentration of inhibitor, and it will approach the same value of Vmax. And for some high concentration of inhibitor, this would be like going this way, but also it would like asymptotically converge to the Vmax. And as I mentioned, that if you look at the Vmax half, which is somewhere here, then here is the Km of uninhibited reaction, here is the Km with some low concentration of inhibitor, and this is Km with some higher concentration of inhibitor. And we can also look at it and this reciprocal plot. So at the reciprocal plot, we got in standard kinetics like these are values. Here is 1 divided by V. Here is 1 divided by concentration of substrate. Here is 1 divided by V max. And here is minus 1 divided by Km. So this Vmax would be the same for inhibited reaction. I will again switch color. So for inhibited reaction, I should keep the same color as in the previous example, sorry. So here this would be uninhibited reaction in a black color, and here are some values measured. So with in the presence of small concentration of inhibitor, it's inhibitor, so this rate is going to be smaller. So it means that reciprocal rate is going to be larger. So it will go like this way. And we get to some point minus 1 divided by Km prime, which is going to be also less negative than for uninhibited reaction, which means that Km is larger. And if we go to further higher concentration, we should get something like that. And all these points should meet, or all these lines should meet in this 1 divided by Vmax. So if you want to determine this value of Km, sorry, this value of Ki, the most straightforward way how to do it is that you start with like different concentration of substrate and a reaction in absence of inhibitor, and you should measure some points on this curve, and from these points you get Km. Then you do the same with the addition of inhibitor, so you use the same concentration, but at this time in the reaction mixture there is some inhibitor added, so you get some lower values. And from this you get a Km prime. You should get the same Vmax. Of course, like because of some experimental inaccuracies, you are likely to get some slightly different Vmax, and then it's up to your like decision whether it's still like competitive inhibition or other type of inhibition, which I will introduce in a next shortly. But now let's assume that we get more or less the same value of Vmax and different value of Km. So now when we know the Km and Km prime, we know that the Km is equal to Km prime multiplied by 1 plus concentration of inhibitor divided by Ki, and from this you know this, you know concentration of inhibitor because this is what we added to the reaction mixture, and from this we can determine the value of Ki. And when we know the value of Ki, we can somehow estimate whether this inhibitor, which could be potential drug, whether it's useful or useless. So if it's some millimolar inhibitor, it's useless. If it's some micromolar inhibitor, it maybe could be a drug, or maybe it's a good starting point for some real drug. So it could be, for example, somehow, if it's some small molecule compound, it could be somehow modified to somehow make it more polar, less polar, to add some interacting group or something like that. It could undergo some organic chemistry, like a little modification, and if you end up with some inhibitor which is a nanomolar inhibitor, and you are lucky that it does not cause some side effects, that it could become a true drug. So now these were competitive inhibitors. So now let's look at the inhibitors which are non-competitive, and again I will write here an equation that it's enzyme plus substrate gives enzyme substrate complex, and this gives the product. And here the inhibitor can bind to enzyme, like in competitive inhibition. It can bind to the enzyme substrate complex to form enzyme substrate inhibitor complex. Also, these could somehow like interact with the substrate to form this also enzyme inhibitor can bind substrate to form enzyme substrate inhibitor. What is not possible is this reaction, so this is forbidden, this doesn't work. And it's important to say that like this Ki and this Ki is the same, so the Ki is equal to concentration of enzyme multiplied by concentration of inhibitor divided by concentration of enzyme inhibitor complex, and this is equal to enzyme substrate multiplied by inhibitor divided by enzyme substrate inhibitor. So this is equal. If it's not equal, then we would call it something like mixed inhibition, but usually the term mixed inhibition is used for some nightmare inhibitions. So this in a pure non-competitive inhibition, these two Ki values are constant, so there is an equal sign here. And I will not go through all this exercise mathematics to get the Michaelis-Menten kinetics for non-competitive inhibition. As you maybe mentioned, I was a little bit in troubles in the previous example, but I don't want to risk it again, so I will just write you. But if you like, you can try as a homework, or I can maybe try as well if you are somehow super interested. But here it's possible to again we will have this magic bracket, and it will be like V max divided by magic bracket, and multiplied by concentration of substrate and divided by Km plus concentration of substrate. So it means that again, when we look at the standard plot, we got something like this for the uninhibited reaction, and then for inhibited reaction we will get something like that. I do my best to write it as accurately as possible. So in a case of competitive inhibition, this if you imagine like taking this plot in some graphical software where you can something shrink, so it would be possible necessary to somehow pull it this way, so to somehow prolong it this way in a competitive inhibition. But in non-competitive inhibition you have to shrink it this way. So if you imagine taking this box in some graphical software, and then you should take a mouse arrow and you somehow shrink it down, so then you get the same shape but a little bit going down. So here we got again Vmax, but the inhibited reaction approaches the Vmax prime, which is the different value. And if we look at Vmax half, and we get some Km, and then we look at Vmax prime half, and I didn't draw it very well, but if imagine this is 1/2 of this, so we should end up in the same value of Km. So Km doesn't change, but Vmax is again now it's divided by 1 plus concentration of inhibitor divided by Km, which means that Km is not changed by a non-competitive inhibitor, but Vmax is decreased. Again, if we look at concentration of inhibitor equal to 0, then we get standard Michaelis-Menten kinetics. And we can also have a look at the this reciprocal plot, this Lineweaver-Burk plot. So here was 1 divided by concentration of substrate, here was 1 divided by rate, here was uninhibited reaction. I should keep the same color, so I will use black color for uninhibited reaction, and here are some experimental values. So now we will get for inhibited reaction. For the inhibited reaction we will get the same value of -1 divided by Km, this will be the same, but the value of 1 divided by V max prime, and here is 1 divided by V max. So 1 divided by V max prime will be bigger, so it means that V max will be smaller. And again, we can measure like different rates at different concentration of substrate with and without inhibitors. If we see that Km doesn't change, but Vmax does, this indicates that the type of inhibition is non-competitive, and again from this we can calculate the value of Ki, and again we can decide whether this inhibitor is a good or bad inhibitor. So, and finally the last type of inhibition is so-called uncompetitive. So uncompetitive, and it works in a way that enzyme plus substrate forms a enzyme substrate complex, and this can decompose to enzyme plus product. An inhibitor can bind only to enzyme inhibitor complex, enzyme substrate complex to form enzyme substrate inhibitor complex. So this is plus inhibitor, and there is Ki again. And I will again not do the I will not do the like this equation, but I will just simply write it here that it's V max divided by the magic bracket multiplied by concentration of substrate, and then there is Km divided by magic bracket or if you like you can again like multiply both parts by the magic bracket, so you get V max multiplied by concentration of substrate divided by Km plus concentration of substrate multiplied by the magic bracket. Usually this one is more convenient because it shows that like the V max prime is equal to V max divided by magic bracket. I will draw it like that, and Km prime is equal to Km. In previous example Km, or in competitive inhibition, the Km value was increased. Here is again decreased. So now so again we can try to plot it, but this is much more difficult than in previous examples. So here I will again make a non-inhibited reaction. So this is like non-inhibited reaction. This is V max, and here would be Km. And this inhibited reaction is like a little bit, so it will, the Vmax is lower, so it will be something like that, but here it's a little bit like sharper, so it will be, I did my best, so I hope it's possible to see it. Yeah. And it's more interesting in this reciprocal plot. So here we got 1 divided by concentration of substrate. Here is 1 divided by rate. I will switch to black color for uninhibited reaction. and this inhibited reaction is like a parallel I hope it's enough parallel, so it will here will be 1 divided by V max prime, and this is minus 1 divided by Km prime, and it should be like increase these values by the same ratio relative to uninhibited reaction, so that's why this curve is parallel. Just to summarize, we have like a non-competitive inhibition, competitive. No, I should start with competitive. Sorry. So we got competitive reaction, non-competitive and uncompetitive. And what happens with the V max and what happens with Km. So in a case of competitive inhibition, V max doesn't change, so I can write that it's like multiplied by 1, and the Km is increased by that it's multiplied by this magic bracket. In non-competitive inhibition, the Vmax is divided by magic bracket, and Km doesn't change. And in uncompetitive inhibition, both are divided by magic bracket, and the magic bracket is equal to 1 plus concentration of inhibitor divided by Ki. Of course, like the term magic bracket is the term which I have just invented, so keep it like our secret code that we call it magic bracket. So this is how enzyme kinetics works, and this is how we can measure Ki values, and this is very important for us for like testing of some potential new drugs, because what we want to know about a new drug is whether it's like active, whether it works, whether it inhibits enough, and whether it inhibits at a small concentration, and this can be expressed by this Ki. This Ki is really the purest way how to express the like the efficiency of the drug at a really molecular level. There is something which is also commonly used in medicinal chemistry, and which is called IC50. And I would say like IC50 is somehow motivated or initiated by some like pharmacology, that in pharmacology there are very often used these something 50 values. So for example, EC50 is like a concentration of some drug which has 50% of effect of, for example, on some receptor. Or in toxicology, you know LD50, lethal dose 50, which means that it's a concentration of some toxic compound at which some 50% of laboratory animals which eat this compound die. So these are commonly used in pharmacology or toxicology, and something similar is often used in enzymology. So what you need is like you plot here the rate of reaction, and here will be like the maximal rate, but this is not Vmax, but this is maximal rate at certain concentration of substrate, which is constant. And then on this axis you plot a concentration of inhibitor, And usually this axis is a logarithmic. It's usually plotted on in a logarithmic axis. So here you got, for example, some nanomolar concentration, here you got some micromolar concentration, and here you got some millimolar concentration. And then for different concentrations of inhibitor, you can measure the rate of reaction. Here should be like because there should be no zero, so there should be like kind of break in the axis. So you should get again here some like break on the line. So here is uninhibited reaction, and you should get something like this kind of sigmoid curve. So at high concentration, of course, like the enzyme is completely killed. At low concentration, there is not enough inhibitor to inhibit it. But here, when there is 50%, so here you got V, I will call it V0 to distinguish it from Vmax. So this V0 divided by 2, and here we got IC50. And this IC50 is like a value in the, as I mentioned, it's like from this pharmacological motivation. So this is not really, I would say, enzymological value, but rather pharmacological. And it's kind of, I would say this is kind of first look at the inhibitor. And you can often find in literature that if somebody is developing some new drug, then they synthesize series of compounds. You can have some nice like some formula, some structures drawn, and some list of compounds which some medicinal chemists synthesize. They could be slightly different because they want to somehow explore different possibilities, which whether some attachment of some metal group here will increase or decrease activity, and so here you got values of IC50, and all these values have some measured value of IC50, and there could be some like some, for example, 500 micromolar, and here some 5 micromolar, and here some 0.1 micromolar, and here again some 500. So these are useless, as a drug. This maybe, and this is potential nice drug. So for this compound also Ki, so here will be not measured, maybe, so it will be for example 3 micromolar here, and here 0.2 micromolar, and here not measured because, and this is the reason why it is usually like this in some articles, is that if you want to measure IC50, you measure one concentration of you just take one concentration of substrate, and you alter the concentration of the inhibitor. If you want to measure Ki, you have to take different values of concentration of substrate, and at the same time you have to alter the concentration of inhibitor. So in most the simplest approach is to take just inhibited and uninhibited reaction, but usually it's good to measure like this Km and Vmax at different concentrations of inhibitors as well. So this measurement of Ki is a little bit more like laborious and more expensive, and you have to do much more experiments or much more test tubes and measurements to get this single value of Ki. And this is much easier. You have to measure just one series. Here you have to measure 2 or 3 or 5 series of these assays. But this Ki is because it's equal to, for example, for competitive inhibition, it's purely like dissociation constant of enzyme inhibitor complex. So you know how at which concentration the of inhibitor the enzyme is half inhibited, and you get much better like a picture of the whole situation. So that's why this Ki is used to somehow quantify the effect of some potential new drug. I also mentioned that there are some covalent or irreversible inhibitors, and if you want to study irreversible inhibitors, I will not go too much to details because it's a little bit like a special enzymology, and I will not this would like somehow inflate this presentation. I will just simply explain how we can show that some inhibitor is irreversible. So usually it is done in a way that we take on the horizontal axis we use different concentration of enzyme. So we mix like different test tubes in which we add different concentration of enzyme, and then we here measure the rate of reaction and we add some constant concentration of substrate. And in normal enzymes, because there is like V max multiplied by CE is K2, V max is CE multiplied by K2. So, and then if the concentration of substrate is complex, Km is complex, then constant, then simply the rate is proportional linearly to concentration of enzyme. So this should be linear, and of course it starts from 0 because no enzyme, no reaction. So this is how it looks like without any inhibitor. If you add some inhibitor, for example, I should stick to the same colors all the time. So this is uninhibited reaction. So, and now I will switch to blue color. So now we add, for example, competitive inhibitor. So the reaction will be slower, but it will be also here starting from 0, and it will be something like that. Depends on a Ki, depends on the concentration of substrate, and depends on concentration of inhibitor. If we add a little bit more inhibitor, we would get something like that. But now let's have a look to irreversible inhibitor. So this is irreversible. So what we often can get is something like that. It follows that it's like 0, and then from some point it starts to rise, and then it's nicely parallel with this uninhibited reaction. So here it's 0, 0, 0, and then it starts to grow in a parallel way. And how this can happen? So if you imagine like here we got a lot of inhibitor. So this is like the same concentration of inhibitor. This curve corresponds to the same concentration of inhibitor. So we got some like inhibitor molecules. I will draw, for example, 5 of them, and there is just one molecule of enzyme. I will draw it like this, and so they bind to each other, they will form like some dead enzyme. And there will be no activity. But here at this point the concentration of enzyme is quite high, so there will be again like the same concentration of inhibitor. I will write it like 5 I's, but there will be like much more these enzymes. So some of them, this one will bind here, this one will bind here, this one will bind here, this one here, this one, no, more, we need more. So this one will bind here, but there are still some active enzymes, so these enzymes will catalyze the reaction. And when we add more and more enzyme, this will grow like linearly, because all these enzymes which reacted with the inhibitor are already like dead. But if we add some fresh enzyme, there is no reason to somehow be inhibited. So at this point here is the point where concentration of inhibitor equals to the concentration of enzyme. Sorry, concentration of enzyme equals to concentration of inhibitor. So this is kind of like titration, and this like shape of this curve is very characteristic for irreversible inhibitor. More it's like a 0, 0, 0 and then linear. More, this means that the inhibitor is pretty irreversible. If it's somehow like kind of on the borderline between like reversible and irreversible, this would be something like smooth change in this point. So this is the way how we can somehow determine whether the inhibitor is reversible, and this is often used. Of course, like if inhibitor is covalent, it's possible to use different like techniques to determine the covalent modification of the enzyme or of the protein. So for example, mass spectrometry is very popular for this purpose. So now let me just briefly make some short introduction to multi substrate kinetics. So at this point we had like that enzyme plus substrate gives enzyme substrate complex, and this gives enzyme plus product. And there are quite few enzymes which have just single substrate. There are some like some isomerases, for example, or some enzymes which decompose, some decarboxylases, for example. So they would have more products like P1, P2 if they decompose. And to certain extent we can also like understand like hydrolases as a enzyme with just single substrate, because the second substrate is water. Water is everywhere at the same concentration, so it's not very it's almost impossible to somehow like change the concentration of water without affecting the enzyme structure. So it's not a variable here, like concentration of water, something which we can change. So also like hydrolases can be to certain extent seen as enzymes with a like single substrate. But there are many like oxidoreductases, transferases, enzymes with 2 substrates, and there are even enzymes with 3 substrates, like all ligases. They combine 2 substrates and they need ATP to drive this reaction, so they need like 3 or usually ATP. So they got 3 substrates, and there could be even something with more substrates. So it's quite I would not go too much to detail, but I would like somehow briefly explain some basic relationships, or why also this multi-substrate kinetics is interesting. So there are two basic models for two substrate reactions. One is called sequential and one is called ping pong. Like table tennis. And the sequential, usually there is so-called Clarence diagram, where you have such a line which indicates the enzyme. And for example, in this sequential model, so there is an ordered sequential model, which means that first you got a substrate A, which binds to the enzyme and forms like enzyme A complex. Then in the second step, the substrate B binds. So you got A, E, AB. And then there is some chemical change. So you get enzyme with a product 1 and product, I will call the second product Q. And first this second product is released. And at the end this Q is the first product is released and the second product is released, and you end up, so here you got EQ and here you got again just enzyme. So there are enzymatic reactions which proceed this way. There are also enzymatic reactions which are somehow like not ordered, and this is usually drawn by these Clarence diagrams this way. So here you got enzyme, and either A can bind first or B can bind first. There is no specific like order. Then then either B binds here, and then or A binds here. So here you got again like EAB. Then from this you got EPQ, and then either P is released first and Q second, or Q is released first and P second, and you end up again with the enzyme E. So the only difference is that here in this first model it's like ordered, so there is first A and then B, and in the second model it's not ordered. You can imagine like from the structural point of view, so if you have some enzyme with some binding site which is like some cavity, and first there is A bound and then B, it will go by this sequential model, because it's not possible for A to somehow get inside if B is bound. But if you have an enzyme with such a binding site like this, so here then A, and this is binding site for A, binding site for B, so they can bind like independently on each other. So this was a sequential mechanism, and the ping pong mechanism works in a way that again I will draw this line which corresponds to the enzyme, and first the substrate A binds, but then the product P is released, and then the substrate B binds and the product Q is released. So because it's like this way, then it's called ping pong, like from one side to another. And let me show some examples. My favorite class of enzymes are glycosidases. So if you imagine some sugar molecule, I will draw here just OH like to indicate that it could be any sugar, so it should be somewhere in the middle of the ring. So and there is some aglycone bound here. So there are enzymes which can hydrolyze this bond in two different ways. So the first one is, I will just switch so that so this kind of sugar or glycoside binds to the active site of the enzyme. Here are some interactions which bind it, and then here should be some either aspartic or glutamic acid residue with which is at the beginning protonated, and here is another glutamic or aspartic residue which is deprotonated. So now what happens is that this proton, I can try if I can erase. I will erase. Okay, so this proton comes here. This bond is erased. This minus goes here, and here a bond is created. So now this aglycone HOR is released and can and it's dissolved in the solution. And instead of this HOR, in the next step, water comes in. So I will draw it like HOH, sorry. And then this proton goes here, this oxygen binds here, and then this bond is broken. So again you end up like this is protonated. Oops, sorry, this is like covalently bound. This bond is erased, and here is again minus, and then the sugar is released. So we had like glycoside OR. First there was bound to the enzyme, then HOR was released, then water came to the active site, and then the sugar was released, GOH. This G indicates like this sugar, for example, glucose. So this is a ping-pong reaction. And as an alternative, we can have an enzyme which works using this sequential mechanism. So I will erase this. Ta-da! Finished. So I will put it to the original state. So so here was OR, and here this residue should be a little bit like this, because here must be a site for water. So here is a water molecule. And what happens? So first this hydrogen, this proton goes here. So here we will have a minus, and here we will have OH. this bond is broken, this bond is formed, this bond is broken, and here it's formed, and this minus charged ended up here. So the reaction was like I will again draw this Claran diagram. So here we got enzyme, and first we got GOR with water, and then HOR was released, and finally GOH. So it's a sequential mechanism. Usually I would expect such a mechanism to be ordered one. So there are different types of glycosidases. You can find hundreds of different glycosidases because you have different sugars in nature. So you have amylase to decompose starch, you got cellulase to decompose cellulose, you got beta galactosidase to decompose the beta galactosides, for example lactose, you got alpha glucosidase to decompose, for example, maltose, and many others. And some of them work in this first mechanism, some of them work in a second mechanism. So some of them work using a ping-pong mechanism, and some of them work via this sequential mechanism. And I think that enzyme kinetics in this context is very interesting, because it's possible to do some experiments in which, in first experiment, you set concentration of the substrate 1 in increasing from low value to high value, so it will increase, and then concentration of substrate 2 would be constant. And then in the second experiment you can do it other way around, so you keep the same concentration of substrate 1 and you increase the concentration of substrate 2. And if you do such an experiment, what you can learn from this experiment is that you can somehow try, there are some equations for, I will not draw them, and of course I will not try to somehow decipher them, but there are separate equation for a sequential mechanism, for ordered and unordered, as well as for ping-pong mechanism. And from these equations you can, by fitting these equations, you can either support one of these two mechanisms. So you can just simply, by taking an enzyme, putting it into test tube with a substrate and measuring the rate of reaction, you can learn something about this mechanism. And because this mechanism is somehow related to, for example, this shape of the active site of the enzyme, or it could be related to the way how the reaction proceeds, you can learn a lot about the mechanism and about even about the structure of the active site. And this is quite interesting, because usually the technique which is currently used in to determine the protein structure is, for example, X-ray crystallography, but it's very complicated method, quite time-consuming, expensive, and there are many enzymes and many proteins which are kind of resistant to some efforts to determine their three-dimensional structure. And by such a simple measurements, you can not, of course, you cannot get some three-dimensional coordinates, but you can learn some new things about the way how the enzyme active site is arranged, just indirectly, but it may be useful for some application. And in the past it was the main way how to somehow infer some way how enzymes works and how they look like in 3 dimension. And another reason why I started with multi-substrate reactions is their inhibition. So I will again draw here for the last time like this equation that you get enzyme plus substrate equals to gives enzyme substrate complex, and this gives enzyme plus product. And it's quite easy to imagine that you have some compound which is very similar to substrate, so it binds to the same site as a substrate, so there will be enzyme inhibitor complex. So if you imagine like having some, for example, some hydrolase with an active site like this, where there is the binding site for some substrate, which can be somehow cleaved here in the middle. So you simply design some molecule which is very similar to this substrate, but the bond which is in the middle is not cleavable. And it's quite like easy to imagine that some inhibitor acts as a competitive inhibitor, so it's something which is similar to substrate and binds to the same site and competes with the inhibitor for with the substrate for the same binding site. So either substrate or inhibitor can bind, but they cannot bind at the same time. And it's much more complicated to imagine something which is a non-competitive inhibitor, and it's even more complicated to imagine something which is uncompetitive inhibitor, so this reaction doesn't take place, only this one. So in some textbooks you find some pictures like that. So here this is the active site where substrate binds, this is enzyme, and this is the binding site for inhibitor. And this binding of inhibitor somehow allosterically causes that the substrate cannot bind here. Cannot bind here. In my opinion, this is, you can find it in many textbooks. In my opinion, this is wrong. So I think that allostery is something still, like there are several allosteric enzymes with allosteric effect, but it's something not so common in nature. And the second reason why I think this is wrong, that I would expect also some back effect, like that the binding of substrate will somehow influence binding of inhibitor. So at the end, this would be either competitive, because either one or either inhibitor can bind here or substrate can bind here, or some kind of mixed inhibition. But you can find some enzymes with a pure non-competitive and even pure uncompetitive behavior. So in my opinion, the most common example of non-competitive inhibitors is that you have enzyme with some two binding site for the substrate A and substrate B. And now you prepare some molecule which can bind to the binding site B and its inhibitor. So now this inhibitor is non-competitive, it's competitive with respect to the inhibitor B. So these two compete for the same binding site. But this inhibitor is non-competitive with respect to A. So if this inhibitor binds here instead of B, A can still bind. Binding of A will not somehow force E to leave the binding site, but the reaction doesn't take place. So I would say, I would guess, I would maybe bet that if you go to some literature and you would count down all the examples of non-competitive inhibitions, some 99% of them would be this scenario, that you have two substrate reaction and you have a inhibitor which competes with one substrate, so it's a competitive inhibitor with respect to with this first substrate, but non-competitive with respect to the second substrate. And with uncompetitive, I think the story usually looks like this. So you got some binding site like this, where here is the binding site A, here is the binding site B. So now if you prepare some inhibitor which binds to the same site as A, so its inhibitor is competitive with respect to A, because it can bind to the same site, but it's uncompetitive with respect to B, because if there is no B bound, this could look like something like, so here first this B has to bind and then this somehow closes, so E cannot bind without B, and so it competes with A and it binds to the same binding site of A, but it's uncompetitive with respect to B, because only when B is bound, then it can bind, but it blocks the reaction again. So again, I would guess that if you find all mentions of uncompetitive inhibition in the literature, and you make some statistics, again 99.9% of these hits would be this scenario. So two substrate or multi-substrate reactions with such an arrangement. So that's all for the enzyme kinetics, and next time I will make some overview of enzyme assays. So we will learn how to assay an enzyme, how to design an assay for a new enzyme, which analytical chemistry techniques we can use to determine activity of an enzyme, and how to calculate and how to express activity of the enzyme. So that's all. Bye bye.